Welcome to the lecture on protocols and services designed to ensure the security of computer systems. This subject is very important because the bulk of protocols still in use today are more than 30 years old. These protocols were not designed with security in mind. Examining individual layers of the OSI model, we have noted that some security measures are present only from the third layer up. The first secure protocol is the IPsec, which is used by default with IP version 6. Even when there are mechanisms allowing to improve security of a computer system or a computer network, they are often not used. There are a number of solutions, but the number of those in use is smaller still. What could you do to improve the security of a computer network? You could ensure the confidentiality and authenticity of the data sent over the network. You can also make sure that you exchange data with the host you actually intended to, or authenticate the remote computer. Doing these three things would improve security greatly. Data confidentiality and authenticity, and the identity of the remote computer can be ensured by implementing the Secure Internet Protocol, or IPsec. Actually, this is a whole suite of protocols. We will now examine each of them individually. The first and most widely used is the ESP protocol, encapsulating security payload. All the protocols that make up the IPsec operate at the third layer of the OSI model. One of the basic advantages of the ESP is that the protocol will not affect in any way the functionality of applications running in a given network. The IPsec can be enabled from the third layer and not from the session layer or higher. We can secure communication between hosts or groups of hosts in a manner not requiring any changes to the infrastructure and software running on your network. ESP is used for encryption and digital signing of the transmitted data. If you use both features of the protocol, the data will first be encrypted and then the cryptograms will be digitally signed. The implementation of ESP required to add the ESP header to the IP header. The first header field contains information about security parameters and about security associations negotiated for the protocol. The header also includes the package sequence number. This means that the IPsec and the ESP protect against replay attacks. In a replay attack, the attacker uses a stolen password instead of cracking one. The ESP automatically eliminates this threat. The packet footer contains information about the amount of pseudo-random data needed for the encryption with a given algorithm. Encryption algorithms have certain requirements concerning the amount of data to be encrypted. The information about the amount of data that was supplemented is sent too. The final part of the header contains the information about the protocol protected by the ESP and the information confirming the identity of the remote host. The ESP protocol can operate in one of two modes. The transport mode is used most often. This is the mode shown in the diagram below. Its function is to ensure the confidentiality and authenticity of communication between two hosts. Everything that is above the third layer of the OSI model gets encrypted. In addition, the ESP header is signed as well. The authenticity of the header is verified. The second mode is the tunnel mode. In the picture below, you can see its schematic representation. This mode is used to secure the communication between routers, that is to say, between subnets. The same kind of data that is encrypted and signed in transport mode is encrypted and signed in tunnel mode as well. In addition, the IP header is attached. The original IP header is replaced with a router header. The router establishes a secure connection channel between two networks. The second protocol of the IPsec suite is the authentication header. It allows you to confirm the authenticity of data and the protocol headers contained in this data. Authenticity is confirmed by attaching a signature to the data being transmitted. We had a chance to examine this when we discussed calculating SHA-1 or MD5 file hashes. Thanks to this, any change in the data will change the hash value. In IP protocols headers, there are fields the values of which are inherently variable. An example of such a field is the TTL, time to live, whose value is reduced by 1 for each router through which the packet is transmitted. If the TTL field was signed, its endpoint value would certainly not match its initial value. A solution to this problem is that all header fields with variable values are reset before getting a signature. This information must be recorded at the AH protocol header. In the header, you will find, for example, the information about the protocol of the package whose data has been protected by the AH protocol. Moreover, there is also the information about the data length and security parameter index, that is, the information about the IPsec security association. This is the information concerning the hash function that has been negotiated and used. As in the case with the ESP, you also find the sequence number of the remote host and its credentials. The authentication header, just like the ESP, can run in one of two modes. A similar transport mode is used to confirm the authenticity of communication between two hosts. In the picture below, you can see all the data except the variable header fields are signed. The tunnel mode is used to confirm the authenticity of data transferred between networks. In this case too, the IP header, with the address pointing to the router that sent the packet, is added. Data can easily be encrypted and digitally signed as long as both communicating parties have access to the shared secret. The problem is how to establish a shared secret key over an insecure communications channel. In the case of the Secure Internet Protocol IPsec, this problem has been solved by the Diffie-Hellman protocol. This is a protocol for the exchange of cryptographic keys using asymmetric key encryption scheme. The designers of the solution also took into consideration the PFS, Perfect Forward Security rule. According to this rule, disclosure of the key should not allow access to all the data encrypted in this key, regardless of whether the data has been encrypted before or after the key was disclosed. This is a simple requirement to meet, and the solution is not technologically complex. The key must be dynamically generated. The master key is used to secure the establishment of one or more session keys. The Diffie-Hellman protocol is computationally complex. If it was used regularly, it would have a perceptible impact on the efficiency of IPsec communication. Moreover, it cannot be used repeatedly for a long time because it would fail to meet PFS requirements. To create an efficient and secure solution, it was decided that the IPsec security associations would be negotiated in a two-phase process. During the first phase, a secure connection is established. The identity of the remote host is verified and the secure channel is set up. Phase 2 is very fast and computationally cheap, but it only allows to renegotiate security associations and replace the session key.